Hello everyone, welcome to the teaching show. In the last video, we had seen that if you have a single component system in which two phases coexist, then given by Gibb's phase rule, you have degree of freedom that is equal to 1. That means if you specify only one intensive variable, then you completely define the system. Okay, so let's understand this concept better by using phase diagram. Here I have drawn a representative phase diagram of any pure component. Okay, so in this case what we see is that the regions, okay, this is a PT plot, that is pressure against temperature. Fine. Now these regions, they correspond to your solid phase, liquid phase and a vapor phase. Okay, so if you have any pure species which exists as solid, so it will the corresponding the point, it will lie on PT plane somewhere in this region. Similarly, the liquid, it will lie somewhere here, vapor, it will lie somewhere here. Okay, and what are these lines? These lines, they basically give you the phase boundaries. That is, this is the boundary where the solid and the liquid phase coexist. So basically these lines are nothing but your coexistence, phase coexistence lines. Okay, so when I am talking about this line, solid and liquid, it coexists on this line. This is known as fusion curve. Over here your solid and vapor coexists. This is your sublimation curve. Along this line, your liquid and vapor coexist. So this is your vaporization curve. Okay, let's apply phase rule to pure solid or liquid or vapor region. Okay, so over here I have only one phase, one component. So 1 minus 1 plus 2. So your degree of freedom is 2. Okay, so when I am dealing with pure species, okay, and I have that in entirely one state, either solid or liquid or vapor, okay, then in that case my degree of freedom is 2. That means I have to specify two intensive variables in order to completely define the system. Let's understand this. Let's say, suppose I have liquid corresponding to this point. Okay, so in order to fix this point, because this is a 2D plot, I have to fix both the pressure as well as temperature. Okay, so I am fixing two intensive variables. Once two intensive variables are fixed, then I can completely define the system. I can calculate all its properties. Fine. Now let's apply once again this phase rule for these phase boundaries. Okay, wherever the phase is changing. Fine. When the phase is changing, that means two phases are coexisting. In that case, we had seen in the last video as well that you have one component and there are two phases which are coexisting. So 1 minus 2 plus 2. So I have degree of freedom equal to 1. Okay. So that means if I fix one of the variable, let's say if I fix my temperature, then my pressure is automatically fixed. But because it has to lie on this phase boundary, or it has to lie on this coexistence line. Okay, since it's lying on this line, as soon as I fix either temperature, pressure gets fixed, or if I fix pressure, the temperature gets fixed. Okay, so that's what I meant, that if I fix temperature, fine, then I am fixing one intensive variable, then my pressure automatically gets fixed. This pressure, okay, this is your vapor pressure. So because your vapor and liquid, they are coexisting at this point, whatever the pressure which is exerted by the vapor phase, that is equal to your total pressure. When you are handling a single component system, then if you have two phases which are in equilibrium, then the vapor pressure, that is equal to the pressure of the system. Okay, so understand this point. Let's further understand this diagram by taking an example. Let's say, okay, for water, it has a certain anomalous behavior. This line, it's not tilted over, it is tilted like this. Okay, so now this becomes a phase diagram for water. Now this is ice, or this is solid water, this is liquid water, and this is water vapor. Okay, let's say I start with ice. Okay, I am starting from this point. I start heating the system. So let's say that the temperature initially of the ice was minus 20 degrees centigrade. Now I started heating it. The temperature rises. Up to what point it will rise? Okay, let's fix that this pressure is now my atmospheric pressure. Okay, so 1 atmosphere, we know that ice starts to melt at 0 degree. So the temperature will rise from minus 20 to 0 degree until it reaches this fusion curve. Over here what happens? Ice starts to melt. Once ice starts to melt, you can take a thermometer and dip into that melting ice. You will see that unless and until the whole ice, it has melted away, the temperature remains fixed at 0 degree. Okay, so whatever heat you are applying in order to melt the ice, it goes in as the latent heat of fusion. Okay, so whatever the heat you are supplying, it goes on into melting the ice and your temperature remains constant. So whenever there is a phase transition which is taking place, it happens if you have fixed the temperature, okay, then the pressure gets fixed, or for that case, for this example, if I have fixed the pressure, that is the atmospheric pressure, then my whole phase transition, it will take place at a specific temperature, okay, corresponding to this point, and this happens to be 0 degree. Okay, now once the whole of the ice has melted away, then you have only liquid water which also lies on this point only. Okay, from here, now at constant pressure, if I start increasing the temperature again, the water will start getting heated up. Okay, so it will heat up to 100 degrees centigrade, because I am doing this experiment at 1 atmosphere, so it will heat up to 100 degrees centigrade. At that point, what you will see is that now the liquid starts to change into vapor. Okay, liquid will start to change into vapor phase, and unless and until whole of the liquid has changed to the vapor phase, the temperature of the system will remain constant at 100 degrees centigrade. Okay, you can see that if you boil water, put the thermometer at 1 atmospheric pressure, your temperature of the boiling water will remain fixed at 100 degrees centigrade. Okay, so what we have learned from this is that whenever first of all, if you have two phases which are coexisting, then they lie on these lines, okay, which is a coexistence region. Okay, this is a coexistence line, sorry, not region. So this is the coexistence line of two phases. Okay, over here, because this is a line, if I fix one point, the other point automatically gets fixed. So that's why degree of freedom is only 1. As soon as I fix temperature, pressure gets fixed, that is the vapor pressure, or if I fix the pressure, then the temperature gets fixed. Okay, so that's what we understood last time. So one more thing I will tell you is that if you are doing it on atmospheric pressure, then this is known as your normal boiling point or normal freezing point, and so on. Okay, so now you understood that whenever you have two phases which coexist, then they lie on this line, okay, where the degree of freedom is 1. Fine. So what we have seen now is that if you have your temperature fixed, then you can calculate your vapor pressure, or vice versa. And one of the equation we had seen last time, what was that? It was your Clausius-Clapeyron equation, in which we said that okay, if I fix the temperature, I could calculate the vapor pressure. Now there are two more methods. One is calculating the vapor pressure using Cox chart, and the second one is Antoine's equation. So let's first see quickly what is Cox chart. Okay, now we had seen that vapor pressure, it usually does not vary linearly with temperature. Okay, what happens is that if I try to come up with a plot of various substances, let's say I am plotting vapor pressure versus temperature for different substances, it will be all over the places. Fine. So in order to give the concise information of a lot of species in a single chart, okay, we have come up with a Cox chart. Let's understand this. So what we see is that vapor pressure changes with temperature very sharply and very erratically with respect to different components or different species. But one thing which was observed was that if you take log of vapor pressure, okay, and if I plot it for one component, then the other component, I should not say component, one species, okay. So let's say I am plotting log of P star with respect to T for species 1. Now, if I take another species, let's say 2, okay, it will follow the same trend. That is what has been observed. That log P star versus T for different substances, they usually follow same trends, okay. So if alternatively what I do is that if they are following the same trend, and if I plot log of P star, okay, for component 1 against log of P star for component 2, because they are varying in a similar fashion, okay, if I plot one against the other, I will end up with a straight line. Okay, so what I am doing now is that I am reading log P star value for component 1 and component 2 at a specific temperature, okay, and I am going to plot one against the other. If I do that, what I get is a straight line, okay. So this curve, this is known as equal temperature reference substance plot. Why we call this equal temperature reference substance plot? Because all these points, they are taken at the equal temperature for species 1 and species 2, plus over here what we are doing is that instead of species 2 or species 2, we are taking as some reference substance for which we have extensive data available for vapor pressure against temperature. One such substance is water, for which you have steam tables that are available. Steam tables, usually if you go and see them, if you have not seen them till now, okay, you can just type steam table and that will open in Google for you. So steam tables, there you will see that vapor pressure is given in a tabulated form against temperature, okay. So this data is extensively available, right? So for any particular temperature, I know what is the vapor pressure for water. So I am going to choose my reference substance or species 2 as my as water, okay. So that's why I am referring to as P reference, and now this is in general any other species for which I want to create a Cox chart, okay. So I want to come up with this linear line, okay, for any species, and the benefit of this is that I can draw for any number of species, okay. So this can be species 1, 2, 3, 4, 5. So in this way I can give information about a large number of species within a single plot, okay. So how do I plot such lines now? Let's see, okay. So what I'm going to do is, first of all, I will select any 2 or 3, minimum 2 or 3 or 4, whatever, okay, that many temperature points, okay. So I have found T1, T2, T3. Let's start with only 3 points, okay. So I have chosen these 3 temperature points. Since I have steam tables, I can go and find out what will be the corresponding reference values or vapor pressure values for the reference substance, okay. So I have found out from steam table the vapor pressure for water or the reference substance at these temperatures, okay. Then I will go and measure my vapor pressure for the species at these 3 temperatures, okay. So let's say that, okay, this is P1, this is P2, this is P3, fine. Now I will go and plot one against the other, fine. So I will plot one against the other. So suppose I get something like this, not that much curve, okay. I have got these 3 points, something like this. So I will try to make a straight line which passes through all these 3 points, okay. And now I have got my equal temperature reference plot. But okay, now if I have to find out the vapor pressure at some other temperature point which I don't know, then what I have to do is simply at the temperature I have to go and find out from steam table what is the vapor pressure of the reference component, that is the water, and then find that point over here, go and read on this line what is the vapor pressure for the unknown species. Okay, but every time going to the steam table, reading the vapor pressure for water, it might become tricky. So what is done is that usually this scale, it is changed from vapor pressure to temperature. Let's understand how this is done. Okay, so this is log scale. So I'm going to mark this as, let's say, 0.1, 1, 10, 100, 1000 and so on. So this is like my pressure in whatever pressure units, let's say mm of Hg. Okay, now I will just go to the steam table and find out what this one mm of Hg correspond to what temperature, and so I will construct another scale on which I will mark my temperatures. Okay, so let's say -5, 0, 5, 10, whatever. So I have now converted this vapor pressure scale of water to temperature scale. Okay, now the things are very easy. I have a plot of temperature versus log T star. So for any substance, see, so this is your Cox chart, and on Cox chart I have different straight lines for different components. Okay, whatever the component, let's say I have benzene, I want to find out my vapor pressure at, let's say, 10 degrees centigrade, then I will just go and read this. Okay, so these are your Cox chart. They are constructed from your equal temperature reference substance plots. Okay, I hope you understood it. And one more thing which we use is Antoine's equation. This is probably used in industry a lot, but Antoine's equation is one thing which you are going to use in this course. So I am going to take an example using Antoine's equation. Okay, and that is your problem 6.2 unsolved from Felder. Fine. And first of all, let's write down Antoine's equation, and this is an empirical equation. Okay, and it takes the form of log of 10 P star, that is equal to A minus B upon T plus C, where A, B and C, they are some constants. Okay, and if you go and see in your book by Felder, this is given in table B4. Okay, so you will have lots of compounds which are listed here: ethanol, chloroform, benzene, whatever. Okay, and corresponding to that you have values of A, B and C which have been listed. Okay, so if you want to find out your vapor pressure for any component, pure species, okay, what you have to do is that just find that species wherever it is, find out these constants, use it to calculate your vapor pressure. One thing you have to keep in mind, in book by Felder, the pressure units are, it is in mm of Hg, and your temperature is in degree centigrade, and this is log to the base 10. Okay, if you go and search it on internet, you might find constants for Antoine's equation which are in different units. Let's say this can be in ln, okay, or the units can be Pascal or kilopascal, temperature can be Kelvin. Okay, so whenever you are using Antoine's equation, make sure what are the units of P and T, and whether this is your log to the base 10 or your Neperian base. Okay, so you have to keep this in mind when you are using Antoine's equation. Other than that, it is very simple and straightforward. Just read these values, plug in over here and find out the value of the vapor pressure. Okay, so let's take now an example which is 6.2 in Felder. It deals with, what it says is that you have a system. Okay, so I have this flask which is 3 liters and I have chloroform in it. I start to heat it until the whole space, the air is driven out, and this whole space, it is filled with only chloroform vapors. Okay, chloroform is CHCl3. Fine. Now what I do is that I close this container. Now this container, it contains only pure species, which is chloroform. I leave it at 30 degrees centigrade and allow it to equilibrate. Okay. After equilibration, that is after the system reaches equilibrium at 30 degrees centigrade, what happens is that the liquid which is present is 10 ml, and this question asks you to calculate, first of all, what is the pressure of the system. I have to calculate the pressure of the system, and second thing is they ask us to calculate what is the mass fraction of the vapor which is present. Okay, so I have to find out XV. Fine. So let's get started. The first thing which is very easy, which is the calculation of the pressure. Now remember your phase diagram. What we said was, okay, so on the phase diagram, I am somewhere on this line. Okay, because I have liquid as well as vapor, so that directly tells you that this is a system in which two phases are in equilibrium. So this lies on this coexistence line. Okay, somewhere on this coexistence line. So whatever will be the pressure of the system, that will be equal to the vapor pressure. So I have to find out the total pressure of the system, that should be equal to your vapor pressure. I am going to use this Antoine's equation to find out the pressure. Okay, so log to the base 10 P star. Now we have to go and read these values. If you go and see the Felder, or if you don't have Felder, just type in Google Felder appendix or something like that. Those tables will open up for you. Okay, so this is table B4. So go and check that. Table B4. Okay, and I am directly taking the values of A, B and C from there and putting it in the formula. So you can go and do it. Okay, 6.90328 minus 1163.03. This temperature is in Celsius. Okay, so I am going to put 30, and the value of C listed over there is 227.4. If I solve this equation, the value of P star, it comes out to be 242.60 mm of Hg. Okay, so my P star, or that is the vapor pressure, is this much, because this lies on this coexistence line in which the vapor and liquid are in equilibrium. So whatever is the pressure of the system, that is equal to the vapor pressure. Okay, for the pure substance. So I am going to directly say that the pressure of the system is equal to vapor pressure, and that is equal to 242.60 mm of Hg. Okay, now I have to calculate the mole fraction of the, mass fraction of the vapor phase. For that I am going to assume that vapor phase follows ideal gas equation. Okay, that's a fair enough approximation. So ideal gas law, I am going to write P1 V1 upon, I am not bothered about R1. Okay, so this is N1 T1, that is equal to PS Vs for 1 mole. Okay, Ts. So this is the form which I am going to use, because I don't know the value of R. We had seen this in my video on ideal gas, how and when and how to use it. Excuse me, you can go and check that video. So I'm going to just plug in the equations. So my pressure for the system, it came out to be 242.60 multiplied by volume. Okay, so what is the volume? I have 10 ml of liquid which is left. So 3 liters, that is equal to 3000 ml. Out of that, 10 ml is liquid, so vapor phase is 2990 ml. N1 I don't know how many moles are there in the vapor phase. T1 I know, the temperature is 30 degree. Because this is ideal gas, always convert this temperature from Celsius to Kelvin scale. Okay, so this is 303. Now I am going to put my standard pressure, standard conditions. So at 1 atmospheric pressure, that is In terms of mm of Hg, that is 760 mm of Hg. Okay, volume is 22.4 liters, but here I am using in ml, so I am going to convert that and write 22400 ml. Okay, that is my volume of 1 kilomole at STP, 1 mole at STP. Okay, divided by 273. So if I solve this, my N1 value is equal to 0.0384 moles. Okay, now I have been asked to calculate my mass fraction. For that I require molecular weight of chloroform, plus I also require the density of chloroform, because I don't know in terms of weight how much 10 ml weighs. Okay, so I need to find also the density. So I need to find molecular weight and density, and in any table, usually these are allowed in exams if their value is not given. Okay, but you can go and check your table at the back of the book where physical properties are listed. Okay, and you can read it from there. So molecular weight of chloroform, that is 119.39 listed value, that is grams per mole, and density of chloroform is listed as 1.489 grams per ml. Okay, so if these values are given, then I can calculate how much is the mass of the vapor and how much is the mass of the liquid. Let's first calculate mass of the vapor. That is equal to these many moles multiplied by this. Okay, so N1 into M, that will give me the mass of the vapor, and it comes out to be equal to 4.58 grams. Similarly, this 10 ml multiply with density and I get the mass of the liquid, that is equal to 14.89 grams. Okay, now I can find out XV, that should be equal to MV upon ml plus mv, and that is equal to, if you plug in the values, 0.235. so this is grams of vapor per gram total. Okay, so we have solved this problem. I hope you understood this, how to use Antoine's equation, because that is the equation which we are going to use quite often. So go and check these tables where the constants are listed, and also check the table for the physical properties. Have a hand on it, feel of it, how to read all these values and use it in your numericals. So I hope you liked this video, and thanks for watching. If you have not subscribed till now, please subscribe to my channel, and don't forget to like the video. Thank you so much.